Great. Thank you, everyone, for making it to one of the last talks of KubeCon. I really appreciate you sticking around. I know there's been a lot. It's been a long week. Really appreciate you coming to listen to us talk about multi-cluster inference gateways. My name is Rob Scott. I work on all kinds of gateway API things and GK networking things at Google. And I've got Daneyon with me.
And I'm Daneyon Hansen. I'm a principal software engineer at Solo.io. And have been involved in Kubernetes networking pretty much from the start, and I'm a maintainer of the Gateway API Inference Extension project, and excited to get into multi-cluster inference gateways with you. So before we dive into multi-cluster inference gateways, we thought it'd be a good idea to kind of build a foundation knowledge. So let's start from the beginning, in a sense, and that is, why do we even talk about inference gateways? Why did we create inference gateways? And at its core, the reason for that is we're dealing with a very different traffic type than what we usually deal with, right? With web requests, they're small. We're measuring them in a matter of milliseconds. We could run them in parallel. And with Gen AI traffic, very different traffic type, right? We're typically dealing with much larger requests, especially when we're talking about multimodal models or multi-turn chat traffic. And so because we have a different type of traffic, we need a different type of solution. And that brings us to inference gateways. And so what is an inference gateway? An inference gateway is a gateway like a proxy or a load balancer that is coupled with an endpoint picker extension, or what we call an EPP. The project, Gateway API Inference Extension, has a reference EPP, but as long as the EPP follows this EPP protocol specification that we defined, you can develop your own EPP if you wanted to. And as part of the gateway, it needs to understand Gateway API, and of course, it also needs to implement the EPP protocol specification. And let's dive a little bit into the EPP. At the heart of the EPP is the scheduler. This is the brain of the EPP that makes the decision on where to route the request to across my fleet of model server replicas. And it is extensible. And at the heart of the scheduler is these plugins that either filter out requests or score the request. So if I have multiple replicas of my model server and I need to make a decision which is the best replica or which replica in that replica set is the best to handle that request, I use these filter and score plugins to make that decision. And not only does the inference gateway need to understand Gateway API and have the EPP protocol spec, but it also needs to understand this new resource that's part of the project, inference pool. And that's how you logically group together your resource, your compute resources. So common set of GPUs, common set of base models would make up your inference pool. And just to call out, inference pool, as of the 1.0 release about 2 months ago, GA'd. So we've put a lot of time into making sure that this API is stable so it can be used with confidence. And we purposely made sure that when we created the inference pool API, that it was very minimal so that we wouldn't introduce breaking changes and that we can adapt it over time based on future use cases. And if you're familiar with the service API, you'll see the inference pool API, a lot of commonality there, where we're using target ports to define what destination port to route the traffic to the backend model server. We use selectors to discover which backend pods comprise the inference pool. And then there's an extension ref, and that is for discovery so that the gateway understands how to discover where does that EPP component live. How do I talk to that EPP? And so at a high level, this is what a request looks like. And even before a request comes in, we see we've got our gateway, our EPP, and then our backend pods that are part of the inference pool. And even before a request comes in, that endpoint picker is scraping the backend model servers with scraping metrics from those backend model servers to help it determine what is the best model server to route the request to, right? And when a request comes in, the gateway would typically go ahead and route that request to the backend pods using kind of traditional load balancing mechanisms if it's least load, round robin, but instead, the gateway is configured to go ahead and send that request to the EPP and let that scheduler within the EPP tell the gateway what is the best endpoint within the pool to route the request to. And here are some benchmarks that we have performed and benchmark testing that we do before every release. On the left-hand side, you're going to see traditional load balancing. This is like Kubernetes service-based load balancing. On the right-hand side, you're going to see inference gateway-based load balancing. And the top graphs you see, that's based on KV cache utilization. And what you see here in the upper right-hand corner when you're using inference gateway is that the utilization of the KV cache is much more uniform. And what does that mean? The requests never get queued. And when the requests never get queued, the responses are much faster. So our tail latency, time to first token, is much faster, much lower than what you would get with, and compared to typical load balancing. So now with that level set, why multi-cluster inference? Right? And so very simply is GPUs are very expensive and scarce resources. Even processing tokens, generating tokens are very expensive. And there's no single cluster that can handle peak requests. And so we need an intelligent multi-cluster layer that understands utilization of those GPU resources, our inference pools across all of our clusters to help us make better utilization of those very expensive resources. With that, I'm going to hand it over to Rob to talk about APIs.
Yeah, so for those of you who have known me before, I spend a lot of time on APIs, and so, of course, I'm going to talk about APIs, I'm sorry, but it will help provide a little bit of background for how we got to this point. So if you think about the APIs that are relevant here, of course, there's going to be Gateway API. Any folks here using Gateway API by any chance? Any more considering using Gateway API sometime soon? Okay, great. So Gateway API is kind of the foundation for all of this. It provides the L7 routing capabilities, that's Gateway, HTTP route, and a whole lot more. And then because this is multi-cluster, the only multi-cluster networking API that's existed so far is multi-cluster service. And then multi-cluster gateway is kind of the combination of those two things. So let's just do a very, very high-level overview of what these are. So first off, Gateway API, I really think of it as having these three different layers here, right? So you've got a gateway, which is kind of a front end into your system. This has IP and ports, basically, and it says I want to listen on HTTP on port 80443, et cetera. You've got a routing layer, which allows you to configure routes to target your backend. So I want to configure all traffic matching this path or query param or header to go to this specific backend. And then I've got a backend layer, and that's where we're going to be focusing. So far, most people who have used Gateway API have focused exclusively on service as a backend layer and didn't really think, well, maybe there could be other kinds of backends. When you add in inference, well, you just switch out one of those backends. Instead of them all being service, you have an inference pool there, right? So inference pool is a different kind of backend inside Kubernetes. And the inference pool is where all the magic happens, all the custom routing that Daneyon was just showing. Now, multi-cluster services, just out of curiosity, how many people are using multi-cluster services? Okay, so much smaller group. But with multi-cluster services, the concept is a little bit different. So you have what we call a cluster set, and that cluster set is a group of connected clusters. And so in this case, I just have 3. And let's say you have a service in one of those clusters, and you want to share it with the other clusters. What you do is you create something called a service export that has the same name and namespace, and that says, share this service with all the other clusters in this cluster set. So what that looks like is you get a service import automatically created for you in all your connected clusters, and you can point traffic at that service import, and it's going to send traffic to what we call a multi-cluster service. Despite us calling this multi-cluster service, there's no actual API here called multi-cluster service. The APIs are service export and service import. Now you put that all together and you get multi-cluster gateways. So if we just take a step back, a service is really pointing at the cluster local endpoints. It's if you want to send traffic to endpoints within your cluster. If, on the other hand, you want to target service import, that's meaning target all the endpoints in connected clusters for this service, thus a multi-cluster service. So this has a lot going on, but this is the combination making a multi-cluster gateway. So let's walk through it step by step. We've got a gateway, a route, and it's pointing at a service import. What is that service import doing? It's representing services in your east and west cluster here. So both are exported, both are joined together, and the result is that service import in the middle. So I hate to tell you this, but we're not actually using multi-cluster service at all. But I wanted to show you this baseline because we use all the same principles for multi-cluster inference. So we'll jump into how you put this together for multi-cluster inference gateway. Now, this looks hopefully very similar to the slide we just looked at, but instead of a service export and a service import, you just have an inference pool, and you, instead of having an entirely different service export resource, we just have that little annotation that says, hey, export this, make it part of the multi-cluster set of inference pools, and then we automatically, again, create inference pool imports, and you can just target those from your routes and send traffic there. So very, very similar experience. But remember how Daneyon said there's more to an inference pool than just the pool. There's this thing called an endpoint picker. And when we were thinking about this, there were really two directions we could go. We could have an endpoint picker right alongside the gateway in a central cluster, or we could have an endpoint picker that was with each inference pool, with each local set of endpoints. And anyone have a guess on which direction we want to go? Okay. Yeah, so somebody already knows here, but we ended up with an endpoint picker in each cluster. And this is because each endpoint picker, as Daneyon already mentioned, is very frequently getting metrics from each endpoint in the inference pool to understand what is the best endpoint at this very specific point in time to serve this request. And that requires knowing within a matter of seconds what the state of the model server endpoints are. So it would not scale if we tried to do this centrally. So that's why we have an endpoint picker in each cluster. Now, the natural next step here is, well, if you have multiple endpoint pickers in multiple clusters, somehow the gateway needs to make a choice, right? Like, how do you choose what cluster you send the traffic to? So, how do you actually pick the cluster? And maybe to simplify it even further, how do we pick the endpoint picker, right? Like, how do you go down that level? So, tried to simplify this diagram out, and you've got a gateway, and you've got endpoint pickers. And somehow you have to decide which of these endpoint pickers should I send this request to, and then that endpoint picker will tell me which endpoint within that cluster is best suited to serve that specific request. Now, the answer right now is it's going to be entirely up to your implementation how they want to do this. The most simple thing is just round robin. I'm going to send traffic to this endpoint picker, then that endpoint picker, back and forth. That will work, but it's not going to be as optimized as we'd like. Another common use case would be active-passive, right? I would rather send all traffic to one cluster, and if that fails for whatever reason, I have something ready to fail over as needed or spill over as needed. But what we've mostly landed on is a metrics-based approach. So we already know that endpoint picker is rapidly scraping metrics from each pod inside your inference pool, each model server framework, and it has a lot of metrics. And with those metrics, it actually aggregates them for us. So our gateways can just ask the endpoint picker for metrics, and get an aggregate view of what's happening inside that pool or inside that cluster. So in this case, you can see, well, okay, and again, I've really simplified this. It's not just a straight percentage, but for the sake of this example, you can see, okay, the Western cluster has slightly lower utilization, so let's send traffic there. Now, other gateways, like the GK one in this case, actually have data for each individual endpoint in the cluster. So what they're doing instead is getting each individual endpoint's metrics and then making a decision based on what we see inside each pod, right? So if we see that there's a single pod that has low capacity, a lot of room left over, we might send it to that cluster even if on average that cluster has a heavier load. So these are different options. This is the one that I'm most familiar with right now, but I expect lots of other implementations to take different approaches here. You may ask, well, which metrics do you use? Well, right now we're saying that KV cache has been very effective. We've got some tests that are showing up very positive results, but like everything else in this ecosystem, things are moving quickly. So the most effective metric today may be different, 6 months from now. So it could depend on your use case, but the idea is to make this highly configurable, highly extensible, so that it can grow as the ecosystem evolves.
So Rob covered the endpoint picker selection or cluster inference pool selection. But after that selection's made, the multi-cluster gateway now needs to route traffic to that particular endpoint. The previous slides that Rob showed, this looks very similar, right? And this is what we call direct routing mode. So our multi-cluster gateway will make that selection based on whatever the implementation you use decides, if it's metrics-based, for example. And based on that input, makes the determination where to forward the traffic to. And with direct mode, the gateway will talk directly to the endpoint picker within the cluster that it selects. Right? And with that said, there needs to be connectivity, direct connectivity between that multi-cluster gateway and the local cluster endpoint picker. And the gateway doesn't route the traffic directly to the endpoint picker, right? It sends the request to the endpoint picker makes a decision on which endpoint to route the request to, sends that back to the multi-cluster gateway, and then the gateway, again, requires that direct routing to the pods or the endpoints to then route the request directly to your model server endpoint. We also defined a gateway routing mode. Now, what's different here is, again, based on what Rob shared with you, the inference pool or cluster is selected, and the gateway, instead of routing directly to an endpoint picker to make the endpoint decision and then route directly to the model server pod, it is able to discover the cluster local gateway, right? So as Rob showed previously, is when an inference pool is annotated, there's a controller that dynamically creates this inference pool import resource in each of the clusters within the cluster set. And that resource exposes the cluster local information for each of the clusters within the cluster set. So the cluster name, the endpoint picker information, basically all the information needed for this multi-cluster gateway here in the central cluster, for our example, to make the decision on where to route the traffic to. And so there's really no one model that's better than the other, but we thought that we need to provide optionality. And these are the two routing modes that we defined in the specification. So to recap, right, going full circle, why do we need multi-cluster? We covered that, but now you can see here is when we have this intelligent kind of layer or tier, this multi-cluster inference gateway that knows about all of the details needed to make the most optimal routing decision to these very precious GPU resources that are spread across all of our different clusters. We have that capability with a multi-cluster inference gateway. So what's next? Rob?
Yeah, so hopefully this is interesting to you. There's a lot that you can already do here. So what Daneyon started with, the single cluster inference gateway, you can try that today. There are many, I want to say in the neighborhood of 7-ish conformant implementations of that spec. It's GA, it should be pretty stable. Definitely recommend trying that out. Multi-cluster implementations are coming soon. I can't give you a specific date for GK, but it is coming. There's K-Gateway and Istio have some issues open to track the development that's going on there. If you want support for this in K-Gateway, Istio, or your gateway provider of choice, please let them know. Please comment on the issue, help them prioritize, and keep this work moving along. And then really, please give us some feedback on what we're doing. Are we solving the right problems? Are we missing something as we're going here? So yeah, please try it out. Please give us feedback. But one last thing you might have thought about, like you saw that I showed you two very similar looking things, right? I showed you there's multi-cluster service and there's multi-cluster inference, and you have inference pull import and you have service import. And maybe some of you may have thought, like, this just isn't going to scale. Like, we add another backend and we have new backend import, right? This just doesn't really scale as we start to add new kinds of backends. So you might ask, well, why not use MCS? And I don't have enough time to go into all the details there, but there are a lot of reasons why we couldn't use multi-cluster service for this kind of multi-cluster backend. But we have been thinking a lot about trying something new here. So there's been a proposal circulating that could have a generic kind of multi-cluster backend that could work across different types like this, whether it's inference pool or service or any other future backend type that's in Kubernetes. So there's a proposal in process. It's linked in the slides that are uploaded with this presentation. And there's also just a very, very rough example of what a composite backend would look like. It's very simple, but the idea is a way to combine backends across clusters of different types. And there's a link to the enhancement proposal doc right there. It's still very early days, but if this is something you're interested in, definitely come join the conversation and help make sure that we're heading in the right direction here. Now, there's a lot of communities involved in this effort. I really, really want to thank everyone who's helped get us this far. Daneyon and I are up here on stage, but we're representing a much larger community than just the two of us. This has been a very large effort, and if you want to get involved, Gateway API has a lot of this, particularly the discussion around composite backend will happen there. If you're interested in all this inference gateway discussion, including the multi-cluster inference discussion, you want to go to the Gateway API inference extension, which also has weekly meetings. And if you want even more meetings in your life, because I know we all love meetings, there's another weekly meeting for you. If you like inference, you might even like agentic. And so there's another Kube subproject called Kube Agentic Networking, which has just started up in the past few weeks. If any of these things are interesting to you, we'd love to get some feedback, some input from you. And again, make sure we're solving the right problems. With that, thanks so much. I think we might have a few minutes for questions.
So you had a diagram that showed a central cluster along with east and west. Can you talk about the latency between the central cluster, the eastern cluster, and the western cluster? Because if requests are coming to the central cluster and then being rerouted to a inference pod in, say, west, what impact does that have on the latency?
Yeah, so there's a lot to that. It's a really good question. It's going to depend on the underlying implementation. Anytime you're, let's imagine, like in this example, I'm pretending these are in different regions. That's a common case for multi-cluster. Often you can't find all your GPUs in one place. So let's say these are different regions. In the case, I can speak with the implementation I'm familiar with, which is GK. We're just programming a load balancer in front, so it's not really like it's attached to a central cluster. It's attached somewhere outside of Kubernetes. Within Kubernetes, certainly, like there's a lot of implementations, including K-Gateway and others, where there might be some additional latency. I'll defer to Daneyon on that. But what I would say is, with inference workloads in particular, adding a few milliseconds of latency is trivial compared to the benefit you can find if you get to a place that has capacity. So generally, the very minimal impact that has is significantly outweighed. But
yeah, and I mean, we talked about part of the magic with the EPP is scraping the metrics from the VLM backend servers or other model server frameworks that are supported. I could see a multi-cluster gateway, right, that not only is taking in EPP metrics from the different clusters, but also factors in what you mentioned, right, is what is the latency to get to those clusters as well, and factor that into the decision. And I'd also say, secondly, is like going back to why inference gateway is, again, we're not talking about millisecond type of latency for web traffic. It's a different traffic type. And what we've seen, and I think Rob covered it in his one slide, is utilizing the KV cache, not having to recreate that KV cache for every LLM request is a significant saver when it comes to tail latency. And so that tends to be more important than millisecond latency of what we're going to get between the clusters.
Great question. Anyone else?
Hey, I was just wondering, like, how, I don't know if this was in your slide, but how does the endpoint picker compare to like a traditional load balancer?
Yeah, so, it is very different. It is by design. There's another question back there for later, but it is by design meant to be an extension. We thought about building this into, for example, Envoy, right? Like you could add a custom load balancing algorithm inside Envoy, but the concern was this ecosystem is moving so fast that whatever we built into a more stable platform like that would not stand the test of time. Whereas with Endpoint Picker, it's very intentionally an extension so that you can fork this. You can create your own. You can plug it in and do whatever you want. So if you find that there would be slightly better logic, or you're just, if I could just tweak this one thing, well, you can. You don't have to, change Envoy or Nginx or whatever underlying data plane. You just change this one thing and it works.
Yeah, and to Rob's point, I mean, the load balancer and proxy market, I mean, it's pretty well established, and most environments are already using one. And so instead of saying, hey, let's create something separate, like let's create something that is separate but integrates with existing infrastructure that's already out there.
Yeah, and like speaking of data planes, this extension mode has support by at least 3 data planes already. It's Envoy, Agent Gateway, and Nginx. And so like instead of trying to change all of those data planes, you change this extension and it works. Sorry.
Okay, thanks for the nice talk. I have more like a failover scenario in mind. What happens if the central cluster go down or one of the east-west cluster goes down?
So we haven't covered that in the spec yet. I'll say that. I can say what GK does right now. We have what we call a config cluster model. And what that is we recommend you put all the same gateway configuration in every single connected cluster. And then with a switch, you can say, actually, this is my source of truth. So if central cluster goes down, you can just say, actually, my source of truth for this config is eastern cluster. And all the config just switches over to that, and things should just keep on moving. So that's one solution. I'm sure there are others. That's just the one I'm most familiar with.
Yeah, and as implementations surface, right, that is definitely going to be part of the multi-cluster controller logic, right? In a sense of like being able to send health requests to those EPPs or to the gateways, depending on the routing mode or potentially both, right? And adjusting the score of how it schedules a request, that would be probably the highest factor of adjusting that score to not route the request to an EPP or the EPP's associated gateway if the health response is not as expected.
I think that's our cue.
Yes. Well, thank you.
Thanks so much,
Appreciate it.
everyone.